Solving exponential equations. So first we're going to solve what I consider these are going to be common base equations. So A, 5 to the x is equal to 125. If I want to solve this exponential equation, what I know is I can write them both sides as a common base, that this is already written as 5 to a power, and this can also be written as 5 to a power. So we have 5 to the x is equal to 5 cubed. Which means since they have a common base, I can say that their exponents have to be the same as well. So that means x is equal to 3. This is also a common base. 4 can be written as base 2. This is already written as base 2. And 16 can also be written as base 2. So what I'm going to do is I'm going to write all these factors as base 2. So this is going to be 2 squared times 2 to the x is equal to 2 to the 4th power. I can't set their exponents equal yet because I need a single exponential base on both sides. And this has 2 factors of base 2. So the way we multiply 2 factors of base 2 is multiplication becomes the addition of their exponents, and the base stays the same. So this is 2 raised to the 2 plus x is equal to 2 raised to the 4. Now that it's a single exponential base of 2 on both sides, I can set their exponents equal. So 2 plus x is equal to 4. And subtracting it on both sides, x is equal to 2. So 4 times 2 squared, so 4 times 4 is 16. Notice that 3 factors over here, each one of these things can be written as base 3. 81 can also be written as base 3. So I'm going to write everything as exponential base 3. So 27 is 3 cubed. 9 is going to be 3 squared raised to the x plus 1. All over 3 squared raised. 81 is going to be 3 to the 4th. So I'm going to condense these things by the rules of exponents. So raising powers to powers mean I'm going to multiply these exponents. So this will be 3 cubed times 3 to the 2x plus 2, 2 times x, 2 times 1, all over 3 squared. Multiplying things with the same base means I can add the powers. Now I know I can just cancel these 3's in this here, but I want to show you the rules of exponents. So multiplying becomes the addition of the exponents. So this is going to be 3 to the 3. Well, 3 plus 2x plus 2. The 3 and the 2 are like terms. So this is going to be 2x plus 5. All over 3 squared is equal to 3 to the 4th. And finally, dividing things with the same base means I'm going to subtract the exponents, and 5 and 2 are like terms. So 2x plus 5 minus 2 is going to be 3 raised to the 2x plus 3 is equal to 3 to the 4th. So now that I have everything as an exponential base 3, I can set their exponents equal, and then I can solve. Now, what happens if they don't have common bases? What if I'm asked to solve 5 to the x is equal to 120? Now, we've done something very similar. We did 5 to the x is equal to 125, and I know that x5 cubed is equal to 125. So I know this number is going to be probably pretty close to 3, but not quite there. So I'm thinking something like in the high 2 area. So one way we can do this is we use the inverse operation of exponential base 5, which is going to be log base 5. So I can log base 5 the left-hand side, which means I also have to log base 5 the right-hand side. Now, log base 5 and exponential base 5 are inverses. So what we'll get back is just x is going to be equal to the log base 5 of 120. Now, this is an exact answer, log base 5 of 120, but you can plug this into your calculator if you want its decimal equivalent, or maybe it's a decimal approximation. So the way it's done is this is going to be equal to the natural log of 120 divided by the natural log of 5. Now, I know on your TI 84 that there is a log base 5 button that's hidden in math, but there's a natural log button right here. So if you want to use natural logs to figure out the decimal equivalent, this is its change of base formula. So I'm going to go natural log of 120. I'm going to make sure to close my parentheses because your calculator will put a parenthesis here, so I'm going to close the parentheses. And same thing here with the 5, I'll make sure to close those parentheses. So divided by natural log of 5. And we'll give us about 2.97. So x is about 2.97. So pretty close to what we expected. Now, there's another way to handle this, and instead of using, its inverse of exponential base 5, I can natural log both sides. So let's do a one more time. So if I'm trying to find 5 to the x is equal to 120, another way to do this is use the common base. So I can natural log this 5 to the x, and I can natural log this 120. Now, they're not inverses, so these will not cancel. But what it allows me to do with logarithms is I can take exponentials and turn them into coefficients. So this is going to be x natural log of 5 would be equal to the natural log of 120. Now, this is multiplication here, so the inverse of multiplication is going to be division. So x is going to be the natural log of 120 divided by the natural log of 5, which gives us exactly the same thing over here. I tend to like to use this when I can because it shows the inverse operation of exponential base 5. But sometimes this is necessary, and I'll show you in an example C where we are forced to really use it. Not a common base problem, even though these can be written as base 3s. But 4 is not going to be written as 3 to an integer power. So I'm going to condense like we did before. I'm going to write this as 3 times, 9 is 3 squared. So 3 squared raised to the x is going to be 3 to the 2x is equal to 4. Now this is 3 to the 1 times 3 to the 2x. So this is going to be 3 to the 1 plus 2x. Multiplying things in the same base means that you're going to add the powers is equal to 4. Now, what I can do is I can use the inverse of exponential base 3, which is going to be log base 3. So log base 3 this side. And I can log base 3 this side. Log base 3 and exponential base 3 are inverses. So we'll get the exponent. isolate the exponent. Which means in order to solve for x, I just have to subtract 1 first. And then divide by 2. That's its exact answer. We know we can find its decimal approximation by natural log of 4 over natural log of 3, then minus 1, and then everything else divided by 2. So our last problem is going to solve an exponential equation where both sides are a base to a power, where that exponent is going to have a term of a variable. So C, 3 to the x is equal to 5 to the x minus 2. Hence, I showed you the natural log version of doing this. So if I log base 3 this side, I'm going to get just the exponent isolated. But I'd have to log base 3 this side as well. And exponential base 5 and log base 3 are not inverses, so it's not going to simplify this to the exponent. And similarly, if I try to log base 5 both sides, this won't get simplified, only this one will. So what I'm going to do is I'm going to natural log both sides. I'm going to use the common base. The natural log of 3 to the x is equal to the natural log of 5 to the x minus 2. Remember, the property of logarithms allow you to take these exponents and turn them into coefficients. So this is x, natural log of 3 minus x minus 2, natural log of 5. Now x is stuck inside this multiplication and natural log of 5, so it'd be more powerful if I was able to expand everything, so I can then log of 5 minus negative 2 natural log of 5. Now we're trying to isolate x's, so any term with an x, I'm going to put to one side of the equation, just say the left side. Any term without an x, which is only this term, we'll leave on the right-hand side. So x natural log of 3 minus x natural log of 5 is equal to negative 2 natural log of 5. Since both of these have an x, I can isolate it if I factored it out. Now this is isolated through factoring, which is multiplication. And the way to get rid of this multiplication of the binomial is to divide the binomial. So x is going to be equal to minus 2 natural log of 5 all over natural log of 3 minus natural log of 5. And that's its exact answer. Now when you simplify this thing, if you want to find its decimal approximation, we put this into our calculator, but be careful. Since the bottom's a binomial, don't forget to put this thing into parentheses. So when I plug this in, I get x is about 6.30. So I'll say 6.3. Then we can check. Plug 6.3 into here, plug 6.3 into here, and see if those values are really, really close. Remember that this is just an approximation. This is not the exact answer. But they'll be really close when